Okay, so we have enough review and notation under our belt so that we can state the Gram-Schmidt algorithm. So here's the setup. In order to apply the Gram-Schmidt algorithm, we start with a basis, v1 through vd, of any vector space. The first thing we're going to do is we're going to define new vectors w1 through wd. The first w, w1, is equal to the first basis vector that we start with, v1. That's the simplest one. The next w, w2, is the second basis vector on our list, but we have to modify it because that second basis vector might not be orthogonal to the first basis vector. To correct this situation, what we do is we subtract off the projection of the second basis vector v2 that we start with onto the first w, w1. And here we're using the projection formula that we stated in the previous video. The next vector on our list, w3, follows the same idea. We start with the third basis vector on our list, v3, but the problem with v3 is that it might not be orthogonal to the previous w's. So to correct this situation, we subtract off the projection of v3 onto w1, and we subtract off the projection of v3 onto w2. After subtracting off those projections, that gives us the third w, w3, and that w3 will now be orthogonal to the previous w's. And we continue along in this fashion until we get to the last w. wd is defined as the last basis vector vd, but the problem with that last basis vector is it might not be orthogonal to the previous w's. And to correct that situation, we subtract off each projection of that last original basis vector vd onto all of the w's that we've previously constructed. After subtracting off all of those projections, that gives us our last w sub d, and now all of the w's are guaranteed to be mutually orthogonal. However, those w's, even though they're mutually orthogonal, are not guaranteed to be unit vectors, and to correct that situation, we now define vectors q1 through qd. q1 is the normalization of w1, so w1 divided by its own length. q2 is the normalization of the second w, w2 divided by its own length. q3 is the normalization of w3, and then we keep normalizing the w's until we get to the last q, q sub d, which is the normalization of w sub d. So this is the Gram-Schmidt algorithm. And what pops out of the Gram-Schmidt algorithm are two new bases for our vector space. The first basis is w1 through wd, and that basis is interesting because it is a mutually orthogonal basis of the original vector space. But after normalizing those w's, we get our basis q1 through qd, and q1 through qd is interesting because it is an orthonormal basis of our vector space. So Gram-Schmidt comes in two stages. The first stage produces a new basis, w1 through wd. That basis is nice because it's mutually orthogonal, but it's not quite orthonormal because the w's might not be unit vectors. So after normalizing, we get our second new basis, q1 through qd, and that basis is guaranteed to be mutually orthogonal and all unit vectors. So let's see the algorithm play out in an example. Here, I'm studying a three-dimensional vector space V, and the vectors that I have as my basis are v1, v2, and v3, as written here. Let's apply the Gram-Schmidt algorithm, which again will come in two stages. We'll construct w1, w2, w3. That will give us a mutually orthogonal basis of this vector space. And then we will normalize those w's to get q1, q2, q3, which gives us an orthonormal basis of this vector space. So let's recall the algorithm. The first thing we do is we define w1, and w1 is easy because it's just equal to v1. So w1 is equal to the very first basis vector in our list, 0, -1, 1, -1. The next vector, w2, says we start with the second basis vector, v2, And then we need to subtract off the projection of V2 onto W1. So we have two terms when we calculate W2 here. The second original basis vector, V2, and then we subtract off the projection of V2 onto W1. And here, I did that on some scratch paper, and then I just wrote down the result here. Great. When I do the subtraction, I end up with the vector 1, 0, 0, 0. So that's my W2 here. We can do a quick sanity check at this stage to make sure what we're doing makes sense. What I mean by that is we could check that W2 is orthogonal to W1 by taking an inner product. And here we see that 1, 0, 0, 0 certainly is orthogonal to 0, negative 1, 1, negative 1. So that's great. But this original space is three-dimensional, so we need three W's, so we're not done yet. Our third W is defined as the third original basis vector, negative 10, 14, negative 13, 9. But we need to subtract off the projection of that third basis vector onto the previous W's. So we subtract off now the projection of V3 onto W1, which is this vector here. Again, I calculated this vector on a scratch piece of paper. And then we subtract off the projection of this third original basis vector onto the second W, W sub 2. And I get negative 10, 0, 0, 0. And when I do the arithmetic here, I produce my third W, 0, 2, negative 1, negative 3. Again, we can do a quick sanity check to make sure what we're doing makes sense. This third W3 should be orthogonal to the previous W's. And we see here certainly 0, 2, negative 1, negative 3 is orthogonal to 1, 0, 0, 0. And also 0, 2, negative 1, negative 3. If we look hard enough and do the inner product in our heads, we realize that is orthogonal to the first W, 0, negative 1, 1, negative 1. So we're done with the first stage of the Gram-Schmidt algorithm. We have successfully produced the mutually orthogonal basis of the original vector space V, which is W1, W2, W3. But there's one more thing to do. We want our orthonormal basis, which means we need to normalize all of these W's. So our first vector in our orthonormal basis will be Q1, which is the normalization of W1. So what we need to do is we take our vector W1 and then we divide by its length. Here we can see quickly that the length is root 3. So Q1 will be 1 over root 3 multiplied by W1. 0, negative 1, 1, negative 1. Our second vector, Q2, will be the normalization of W2. But here we realize that W2 happened to be a unit vector, so the length is equal to 1 already. So Q2 equals 1, 0, 0, 0. That's not guaranteed to always happen. We're just lucky in this case. What about Q3? Q3 is the normalization of W3. Here, W3 is 0, 2, negative 1, negative 3. So we'll have to take that vector and divide by its length. Its length should be the root of 0 squared plus 2 squared plus negative 1 squared plus negative 3 squared. So let's see here. That's 9 plus 4 plus 1. So that should be, root 14. So we do take 1 over root 14, and then we multiply by 0, 2, negative 1, negative 3. And that gives our third Q. So after this process, we've now produced a mutually orthogonal basis of the vector space, W1, W2, W3, and we also have an orthonormal basis of this vector space, Q1, Q2, Q3.